Good afternoon, sir.
Good afternoon. Okay,
Good
so
afternoon, sir.
good afternoon. Good afternoon. So I've just started the recording. Just wait a minute. Okay, so today we'll start a little bit of about error propagation. We'll quickly cover certain content, and then we'll go back to the two-dimensional error and three-dimensional error, which we were discussing in the previous class. There is not much content in that 2D and 3D error categorization. We'll cover that later on. So with the error propagation, the name itself is very clear that we are talking about the propagation of errors. Now, what is more important at this point that you should understand that you have blunders, you have systematic errors, you have random errors in your observation, isn't it? Primarily. So once you collected the data from the field, because eventually you have to go back to the field with your instrumentation and everything, and then you collect the data, isn't it? The measurements are observed always on the field with the help of instruments. So if you're working with any kind of instruments, the moment you collect the data, it becomes your observations, and that observation is inherent to those errors. And primarily we were of this opinion that we must take care of the blunders as well as the systematic errors. So when we talk about the error propagation, so we generally are not interested in the propagation of systematic as well as blunder errors, because if they are propagating to other observation, then it is the process itself is a erroneous. That means they should be taken care of before going for any indirect measurements. So obviously the observation or the measurements which for the quantity which you are taking on the field directly, they will be called as a direct quantities. Direct quantities means length of area, width of area, height of area, angle of the area. So for any kind of primarily observation for which you have an instrument to measure those quantities, that will be called as direct quantities. And the indirect quantities are generally a function or a mathematical model which you will be using, where you will give input your direct quantities, and then your output would be the associated measurement for the indirect quantity. So the indirect quantities are generally computed with the help of a mathematical model. So it should be very clear, and there should be no doubt among all of you. If you have any doubt, you just let me know. So there are two things which you should be aware of. One is direct quantities and another is indirect quantities. Okay. So what happened in the case of direct quantities, that you go with the instrument and you collect the data. But what happens, as I've told you, those measurements, be it length or be it width, be it the angle, height, slope, whatever it is. So what is generally they are prone to errors, all three types of errors: systematic errors, blunders, and your random errors. But when we talk about the error propagation, we only talk about the error propagation of random errors, because they are those errors which we are not, I mean, we do not have any control over it. Okay, they are bound to happen, and as if we have discussed, they have a probability of occurrence, isn't it? That the probability of this much error within this limit is this, probability of this much error to be within this is this. So we know that random errors has a probability of occurrence, they have a frequency distribution, they have a probability distribution. Obviously, such kind of errors will, if it is there in the system, they will propagate to the indirect quantities, and that is what we have to estimate, isn't it? Because in the first class itself, I've asked you one question: if error in length and width is 1 millimeter, isn't it? If I've asked you this question, if you have measured length and width with the instrument, and you have error of 1 millimeter in both length and width, what would be the error in the area? And probably all of you was giving the wrong answers. The reason is simple: because you do not have that background to answer appropriately apart from civil engineering students. But still, civil engineering students do not think in that direction too much, and they generally provide the answers with their general acumen, okay, general aptitude skills. But in the case of error propagation of random errors, which we also call it variance covariance propagation, we need to be very careful about how the error propagation is generally being done. So that's why this objective of this uh, particular content, which is to learn various definitions and concept of error and covariance propagation. Please make sure what I'm trying to say here, we are not discussing the error propagation of blunders or gross errors and systematic error. This is a even I mean propagating your systematic error to indirect quantities itself is a blunder. Okay? So you cannot commit it. Okay. Anyways, lecture would be consist of expectation operator, variance and standard deviation, covariances, and then we also discuss about the cross covariance. It's very good quantity. Then error and covariance propagation, followed by little pre-analysis, because we need to understand the importance of office work. Okay, that's very essential that you should know about the pre-analysis. Anyways, we'll discuss much more about error propagation. You will be much more comfortable. Now, what I request right now is that you should be with your pen and your notebook. Those who are, I mean, with on mobile or any kind of platform, just keep it aside. Have your pen and notebook with you, because there will be a lot of derivation which you will be doing right now. So it would be good that if you try to write it down also. So expectation of a random variable, which we have discussed many a times. For a discrete case, it would be represented as summation I is equal to from infinity minus infinity to plus infinity xi, and associated probability of occurrence of the particular xi, which is we also call it as observation. So this discrete is very simple. The continuous case, the summation will be replaced by the integral, and px, that means the individual probability, will be represented by a frequency distribution or probability density function, most probably, and that becomes fxx. So you all know that. So very, in a very general understanding, you are given this term, that in the discrete how it is represented, and continuous how it is represented. Okay, and in fact, if your function gx of a random variable x is available, whose pdf is fx, then this expectation of gx would become minus infinity to plus infinity gx fx dx. So this is a way of giving you a little uh, prerequisite before moving ahead, that expectation operators is something which denotes what is expected from a set of observation. Okay, so if an individual observation is there, what is expected from it? It should be the mean. Okay, then you should know how the mean is calculated. Then the gx1, why the example of a function like gx is given? Because later on you will see the variance is a function of x, and it means your individual observation as well as the mean. So that becomes a function operator, and then we will use those understanding for answering that part. So I mean, you should try to write it down also, for discrete case, for continuous case, as well as for the function case. Very simple, just simple understand. Those who are not following or having little difficulty, but they are not speaking about it, they must know that you are right. And those who are still not comfortable with frequency distribution, they must follow the books and the content which we have discussed, and you can download the recording and you can see it down. Okay, so the discrete cases for the probability, or we could also call it the relative frequency, and for the continuous case we'll have the density function. Okay, then for the two random variables x and y, the expectation operator, which is given as gxy minus infinity to plus infinity, and then gxy fxy xy dx. You need to understand here that the fxy xy is the bivariate normal distribution, which we have discussed in the previous class. So the bivariate density function would be replaced here if any such case would be there in future. But anyways, just for your understanding, if it is a single function variable or a double function variable or multi-function variable, okay, sorry, multi-variable function. I'm just saying a multi-variable function. It is a multi-variable function, not multi-function variable. It is a multi-variable function. Okay, so for n random variables, which is x1, x2, x3, and x4, the expectation
Hello,
operator.
sir.
Yes.
Sir, screen is not visible.
Is it so for all?
No, sir, it's
Yes, sir.
visible to
Visible,
me.
sir.
Visible,
भाई
sir.
कौन
Visible,
किस
sir.
Sir, the expectation page is coming, sir. Page number 3.
नहीं तो आप अपना नेटवर्क फिर से ज्वाइन करिए, है ना, फिर से ज्वाइन करिए. Sometimes it happens in certain networks. So for n random variables, which is x1, x2, x3, and xn, similar, we can repeat it down just like we have written for the first case. Okay, so I hope it is now it is very much clear for n random variables what we are doing. For independent random variables, which is a very peculiar case for our Geo-Informatics, that generally one observation doesn't correlate with another, because every event is an independent event. Whenever you take first reading of length, it is a one value. Then you take another reading of this another event. They both are independent. So when you have independent events, the expectation would be given like this. Just like in the case of probability, the combined probability is the multiplication of the individual probability. So similarly here, the notation for multiplication is coming, and the expectation of x1, x2, x3, x4, and xn is given by this. So very good basic fundamentals. Maybe we'll be using somewhere. We need to understand this part, that when we are talking about the n random variables, then we'll start from the expectation operator, how we are writing. Okay. So properties, just like you have some algebraic properties for random variables x1, x2, x3, and xn, if a new variable z is formed by adding all these random variables x1 plus x2 plus x3 plus xn, then the probability would be given as e expectation of x1 plus x2. So if you could just understand that if n random variables are there or n observations are there, then the addition would create a new random variable, isn't it? Z would be x1 plus x2 plus x3 plus xn. So expectation of z would be given by this. You need to understand at individual point, the expectation of x1 would be mu x1, expectation of x2 would be mu x2, expectation of x3 would be mu x3. Okay. For a constant, expectation of k would become k. Expectation of a constant would automatically come out of that operator, would become expectation of cx would become c expectation of x. For constant g, for constant c and a function of g of random variable x, that is expectation cgx, you can write it down c expectation gx. Very basic equations. There is not to worry about much. Then the two function, be it additive or subtractive, appropriately you could take it down from your previous understanding. Okay. So for random variables x1, x2, x3, and xn, you have such multiplication. So please understand, the moment you are multiplying certain coefficient with your individual observation, the mean would also multiplied with the same observation, the same coefficient. So this is the one thing which is given here as part of your understanding. Okay. So mean is multiplied. Okay, that is one thing which you need to understand. So expectation of a summation of I is equal to 1 to n ai xi would become summation of 1 to n ai expectation xi. Okay. Similarly, the variance and standard deviation. So variance function, as I've told you, the same you could realize from your basic understanding. This variance function, which we call it as Vx, is nothing but expectation. And how the variance is defined? The variation of individual observation from mean, isn't it? That's how we define our observations, our dispersion. So variance Vx is equal to expectation of x minus expectation of x and whole square. That because variance is the variance is decided as the quantity which is individual observation and its deviation from mean and its square. So we are representing expectation of x minus expectation of x square. Okay. And then we can write it down similarly, expectation of x minus mu x square, and that becomes sigma x square. It's very good line, and you should follow it. If anybody is having any slightest doubt, you can ask it, because we are defining the basic element, because your error propagation is totally dependent on these basic quantity. If you are not able to write expectation of x as mu x, if you're not able to write expectation of ax as a mu x, then there is a problem. Okay, I'm just again repeating myself, because this is how everything is written now in terms of slide. Otherwise in classroom we'll discuss much more coherently. But anyways, expectation of x is mu x, which is very well known. Expectation of ax is a mu x. This is very important. You should understand this part, that whenever you have a quantity or a coefficient which is multiplied by individual variable, the corresponding output would be coefficient multiplied to the mean of the observation. So similarly here, your variance function is defined as expectation of x minus expectation of x and then whole square. That's how you write as expectation of x minus mu x whole square would be sigma x square. Now it is a function. As I've told you in the previous gx case, I'm just changed the slide to go back to the fourth set of rule, which is the for a constant c and a function g of random variable x. So expectation of cgx would become c expectation of gx. Okay. Similarly here in this case, what we have expectation minus infinity. Sorry, my expectation minus integral minus infinity to infinity x minus mu x square fx dx. That becomes for the continuous case, and the discrete case is now here the point to be noted here is that x minus mu x whole square is the function gx, is representing as a function gx, just like you have read in your first two slides about variation in the expectation operator, isn't it? So I hope it is very much clear. The standard deviation is obviously the positive square root of the variance. The alternative form, which we are writing Vx as x minus mu x square as sigma x square, then we will open the quantities on the square term. That becomes x minus mu x. Here you would see x minus mu x whole square. Okay, so x minus mu x square would become sigma x square. So x square minus 2x mu x plus mu x square. Now you could probably relate. So I'm just giving you a moment to see the slide so that you are very much clear about the content which is we are using. So expectation of x is mu x. Please remember, expectation of x is mu x, but expectation of x square इसके बारे में कुछ नहीं बताया गया. So expectation of x square is a different terminology. We do not have any such assumption or any such notations for it. So that becomes as it is. Okay. So sigma x square is equal to expectation of x square minus mu x square. I think in one case we have seen this in the basic measurement and errors slide. At that time I told you that when you open it up, you will get the similar value. I'm just giving a moment so that all could follow. If you have any doubt, you just simply ask. Okay.
So, sir, we can write e of x square minus e square of x.
Say again.
E of x square minus e square of x.
Why to complicate? The moment you know ex is expectation of x is mu x. What you are trying is correct, but why to complicate? Just for for what purpose you are trying to say it? Sigma x square as e of x square minus ex square, like that.
Yes, sir.
That's fine. As long as you follow the content, that's fine. Now, most people would be a little in this thought that why we are reading this, isn't it? Because many times it is a very right question that should come to your mind first. The moment you have a slide in front of you, that why we are reading this. Why not directly come to the error propagation? Because these are the fundamental quantities, and you would be writing it multiple times while coming back to error propagation. So the moment I'll ask you to do this, they will start from these quantities only. Okay. So now, if everybody is clear, we can move ahead. Any questions?
Sir, e of x square is equal to second moment of mean. So we can also write second moment minus mean square.
A very less time you will use it. Okay. So similarly, the moment variance comes, you will have the covariance. Okay. So the covariance sigma xy between two random variables x and y is defined as sigma xy, and in bracket you could realize that while writing for variance, you were writing as expectation. Within bracket you are writing x minus mu x whole square. But the moment the covariance concept comes, you know that you have to write as expectation of x minus mu x and another bracket y minus mu y. Okay. This is very basic conceptual understanding that the covariance is, that's how you will write the covariances. Okay. Then again, this become a function of x, y, mu x, mu y. That it becomes a gx. So how will you write it? You will write, because it is a multivariate. You have both x and mu x and y and mu y. You will have to write as a double integral. And the moment you have write double integral, the fxy you should be known, okay, to you. But anyways, on the left hand side, we can open it up. That's just we have done in the previous case. So sigma xy is written as expectation xy minus, you just open it up, and the expectation of xy minus mu x mu y is also used as a interchangeably sigma yx. So generally on non-diagonal elements, if you talk about of a variance covariance matrix, when I say non-diagonal elements, Now you should be familiar because you are following the matrix assignment. That means it is very much clear that you should know what is diagonal element, what are non-diagonal elements, upper diagonal, lower diagonal. You should all be familiar with. So the moment I say diagonal, non-diagonal elements, that means we are talking about the covariances, and obviously with the associated with the variance covariance matrix. So in a non-diagonal element of variance covariance matrix, it is covariances which are written. Okay. So for independent variable, as I've told you in Geo-Informatics, the independence zero correlation would ultimately relate to independence of the variables. So for independent variables of x and y, covariance would become equal to 0. And the moment you have expectation of x, y, and you know that x and y are independent, you can write it down as a expectation of x, expectation of y separately, and that becomes 0. This is a mathematical proof. Now you should be aware and you should feel comfortable that the questions which or the straightforward we have discussed, that when we discuss about the covariance or correlation, it is 0 for independent case in while discussing about the probability distribution. Now it is the mathematical proof which is in front of you. Now you can see why it is 0, because the moment you say they are independent, the expectation operator give you a freedom to open it up again by a rule of thumb. So expectation of xy becomes expectation of x multiplied by expectation of y, and that's how you have mu x mu y minus mu x mu y. That becomes 0. So that is the one difference. So previously we were discussing about the variance. Now you have covariances. Just see it. I hope you are writing it down. See, I mean, you have to write it down because it is not a history class. You cannot follow everything by just by looking. You have to write it down so that you would be comfortable. Because otherwise, in your mid-semester examination or quizzes or whatever we'll be taking, you have to write it down. Okay. So we have discussed the variances. We have discussed the covariance. Now, the ideally would be there would be a one separate page where you would be writing about how to write variances in expectation operator form, how to write covariances in expectation operator form, and at the same time, you should also write how to write mean in terms of frequency distribution or the probability distribution, and the variance in terms of frequency distribution or probability distribution. Just we have discussed in the previous classes. At the same time, you should also write what is the formula for variances, what is the formula for mean in general statistics. But that's how you will be much more comfortable. Now you know how to write the same quantities, statistical quantities like mean and variances and covariances in three different formats. One in expectation operator format, another in frequency and probability distribution format for discrete and continuous case, and third one in general for a statistical case. See, this is why, because that's how we as a student have approached these kind of content. That's how we'll be more comfortable while we looking at these equations, fundamental quantities which are required. Because whenever a data set is there, data set has two fundamental quantities, mean and variances. That tells a lot about the data set before moving ahead and finding out another quantities. Okay. So I hope this is okay. Now, again, the mean vector for multivariate distribution. So again, mean variable for multivariate distribution means, first you need to understand there is a vector x which consists of n independent random variables. Like x1 is, or simply x vector consists of x1, x2, x3, xn. These are the n independent random variables. They have their own set of observations from which they represent as x1. They have their own set of observation from which they are represented as x2. So it is a chain of event. You have a vector x. Vector x is n cross 1, which is x1 to xn. Then individual x1 is another set of observation. That's how you have calculated the mean. So mu x is mu x1, mu x2, x minus mu xn, and then corresponding they would be written as in terms of expectation operator, and in a combined manner you could write it as a expectation of bold x, which is a vector that becomes the mu x. Correspondingly, as I've told you, yes, there is a little class work which you can do right now just to understand for the covariance matrix sigma x. Here it is written as sigma x is expectation of x minus mu x and within bracket x minus mu x transpose. Now what I want is that you let me know why it is not x minus mu x transpose multiplied by x minus mu x, and why it is written as x minus mu x and multiplied by x minus mu x transpose. Why not the other way around? Just try to follow and give me answer. I hope the question is clear. If anyone is not comfortable with the question, I can repeat it down again. See, your participation is very important. Only then will be more comfortable in the advanced content, because there is a lot of good or fundamental adjustment computation basics are there, which you should be aware of.
Sir,
Yes.
sir, because the x minus mu x matrix will be n cross 1 matrix, and x minus mu x will be 1 cross n matrix, and after the multiplication it will become n cross n matrix. If it would have been opposite, then it would have been 1 cross n into n cross 1 matrix. That would not be feasible for multiplication.
Very good. So I cannot see who are speaking. So, but you should be
Sir, Sumit Pandey.
yeah, Sumit. So what is the output from this little discussion is that your variance covariance matrix is always a square matrix. First thing, wrote it down somewhere, because I'll not repeat it many times while we're discussing about the variance covariance matrix. So variance covariance matrix is always a square matrix, consists of number of variables involved. So if a function vector is of n dimension, the variance covariance matrix would automatically will become n cross n. Now what will happen? You are here, I am here. Many times when I ask with the student what would be the dimension of variance covariance matrix, you will see that many students will say, sir, 3 cross 1, sir, 5 cross 1. They will answer like that. It's totally wrong. I'm just again repeating myself. Variance covariance matrix will always be a square matrix. Okay. Please remember, variance covariance matrix is representing the information about the dispersion and the correlation of all the variables in the picture. Okay. It cannot be a single vector. It cannot be a row vector or a column vector. Instead, it should be a square matrix. That is why the present way of writing is suitable. The other way around is not possible at all. So I hope all of you have followed it. We can move ahead with another. Now the covariance matrix, how it would be? This is the opening up. What we have discussed and finalized in the previous slide, it just opened up for those who still had little difficulty. They can see it and try to understand, follow it, because there is nothing new. What we have discussed in the previous slide is again just representing it in a detailed manner. Okay, so any question? So just try to see the diagonal elements are sigma x1 square, the sigma x2 square, sigma x3 square, and sigma xn square. They are called as variances. Variances represent the deviation or dispersion in individual variable, isn't it? We are all talking about x1 here only. The sigma x1 and x2 represent the covariance, or a picture where two variables are seen at the same time, and then it represent how the two are correlated with each other. You are saying that these are the quantities which are written, should have been written as sigma x2 x1 rather than writing sigma x1 x2. So probably this would be written just to make sure that you understand that both are equal. Okay. Next is average precision. Average precision is, that means the trace of the matrix of variance covariance matrix and then divided by n and taken a square root of it. This is called as average precision. Again, average precision is an index that is a scalar function. You can call it as average precision as a scalar function. Why? The scalar function are something which is or you could also say estimated or determined from the matrices given as variance covariance matrix. So we are using the scalar function like trace, determinant, max, min, these kind of things. So they are or norm of a matrix. So see, these are popular scalar matrix, scalar function, I would rather say, that are popularly used in Geo-Informatics. So this is one is called as average precision. Okay, average precision means considering average of all possible variable in the picture. Then obviously after covariance, what comes next? Correlation or coefficient of correlation, which we call as a rho xy. So we know that the standardized or normal random variable is given by zx, which is nothing but x minus mu x upon sigma x, and expectation of two products of standardized variable, and we generally call them as what should I say, the correlation between x and y is denoted by expectation zx zy. And then when you open up the zx and zy, the expectation of a by b is, obviously you should understand that it is expectation of a divided by expectation of b. So that's how you could write it down. That's rho xy is nothing but sigma xy upon sigma x multiplied by sigma y. Okay, so nothing new. So just another extension of covariance. Now you probably would wonder that whenever you read principle of remote sensing, if you read GPS, if you read LIDAR, if you read INSAR, SAR, POLSAR, whatever you read, the variance covariance matrix will not be far behind. It will always be there. Why? Because you are talking about the observations. You won't believe that one of our PhD student, he just used this variance covariance matrix of SAR observable to make sure that a new function or new algorithm could be created based on this very little understanding. If you start with principle of remote sensing, then the optimum index factor will be using it, OIF, to select a pair of band for giving the information. Okay, so please remember that the variance covariance matrix will not be something which you can rule out from the picture. Otherwise Geo-Informatics is nothing but a thematic maps. You just have colored pictures of different area. So geoinformatics is more about how well and how statistically you are saying something, you are commenting something, how you are developing algorithm, novel contributions. Okay. So everywhere these fundamental quantities, mean, variance, covariance, variance covariance matrix, they will always be there. And novel contribution, if you talk about the actual research, that will only come out of the so-called functions, fundamental quantities which you are aware of, and you play with that. The moment you start playing with that data set, then you in a zone where you can contribute something to the scientific community. Okay, then it's very good slide which starts the fundamental for error propagation. Let us just see the linear combination of one random variable. So if x is a random variable with expectation mu x and variance sigma x square, okay. If another variable y is there, ax plus b. So people will ask you what would be the mu y. Let's say first, what will be the mu y, or what will be the sigma y square, isn't it? So what you need to do, you just take the expectation operator on both sides for a function. The first to start with is take the function expectation operator on both sides. The moment you take y is equal to x plus b and take expectation operator on both sides, the left hand side become expectation of y, which is again mu y. The moment you go on the right hand side, it would become expectation of ax plus b. Then you know the formula, expectation of a plus b as expectation of a plus expectation of b. So here you write as expectation of ax plus b as expectation of ax plus expectation of b. Now b is a constant that will come out as it is. So b would come out, but the expectation of ax would become a expectation of x, and it would be known as expectation of x. You know it is mu x. So y is equal to ax plus b would give mu I as a mu x plus b. So you can see it. So very good observation here is that mean value of y or expected value of y, which is mu y, is having everything with it. It is having a, it is having b. That means the mean information is multiplied by the coefficient, as well as a translation vector is also there, which is obviously in the picture. Okay, but the variance doesn't take into account the b. You will see it the moment we'll take the variance operator on both sides. The variance of y will become sigma y square, and that it is written as expectation of y minus mu y whole square. You will replace y as ax plus b, you will replace mu y as a mu x plus b, and you will see b gets cancelled out. Take a look and you will see the answer is sigma y square is equal to a square expectation of x minus mu x whole square, that becomes sigma x square. So just take a look at this. Just take a look at this one. Just take a look. Anyone having any doubt in this? See, if you are seeing it and not writing, then probably at this moment you will understand it. But the moment you will be given the task and you do not have anything to see from, you will probably commit mistakes. So it is better that you should write it. See whether you are able to write it down or not, because very simple mathematics. The moment you know the basics, you can start it down like anything. So I hope it is clear to all of you. Is there any doubt, or if anybody is not able to understand, this is the high time that you should ask questions.
हेलो सर।
हाँ, yes.
सर अभी आपने जो बताया था, अगर हम मल्टीप्लिकेशन करते हैं मैट्रिक्स का, ट्रांसपोज वाली मैट्रिक्स पहले लेके और नॉर्मल मैट्रिक्स बाद में, तो सर मल्टीप्लिकेशन तो फिजिबल है, 1 क्रॉस 1 की बन जाएगी मैट्रिक्स। तो सर मतलब एक्सप्लेनेशन क्या हुआ इसका?
बेटा 1 क्रॉस 1 की बन जाएगी या n क्रॉस n की बनेगी, रिलेवेंट क्या है? If you have n variables, and if you want to ask about variance covariance matrix of a set of random variables that are n, will 1 cross 1 will sufficient to represent it? Answer is no. You cannot represent it by 1 cross 1.
Yes, okay.
Next slide. Then vector x will have the same variance covariance matrix as E, since the true value x is non-random. It is, I mean, the value of x bar, which we also call as the mean, is it is non-random in nature. Okay, so that proof is given here. For that matter, you could try to see. These are the some you know, playing with the same equation, just by telling you that what we are talking about. What is variance covariance matrix? If any one of you are having difficulties looking at this, because yeah, it's true. See, I understand, because see, you are listening it, you are seeing such type of content for the first time. It may looks difficult, but it's very easy. How to become it more you know, understandable? What you can do, you just need to stick to your basic. Call each mathematical quantity which is written by its name. Just like if I ask you, what is this?
Summation.
No, that's blunder. It is not summation. It is variance covariance matrix of x, vector x. There is a difference between summation and variance covariance matrix. You need to understand where you are. If you are in a mathematical domain where you are given certain discrete values and you have to solve it for summation or some kind of, then you can call it as a summation. But here the context is changed. You are in the Geo-Informatics domain reading about the so-called random error propagation. You have error quantities with you. You have expectation operator on it. You cannot blindly say on the summation. Just try to see. It is a variance covariance matrix of x. Summation cannot be written like that. The way it is written, sigma xx. Summation cannot be written like that. It is expectation. The right hand side is expectation, E. It is your expectation. So the variance covariance matrix, it is the left hand side of random vector x. The right hand side is expectation, and expectation, how it is written as x minus mu x, x minus mu x transpose. Now you know expectation of x would become x bar and x minus x bar would become E. Then it is the same. And for that matter, Let us just go back to your basics of variance covariance matrix. I'm just changing the slide. Please be patient.
Sir.
See here, in the case of variance covariance matrix, what it is? These sigma x square, x1 x square, x2 square, x3 square, xn square, they all are deviations from the mean, isn't it? They are all deviation. They are all considered as whatever is not the mean in terms of observation. That means the observation contains error, and that is represented by sigma. What is expected from individual observation? That it is expected from individual observation that it should reach the mean. It should be the mean, and whatever is not the mean is containing errors. Now go back to this slide which we were discussing. What it is on the right hand side? It is again representing the error values in a form of variance covariance matrix. This is what we were talking about. Anything which is not a mean is having error. How do we represent it? X minus mu x or x minus x bar, whatever you call it. And you can represent it by these terminology called E transpose sigma E. So in any way, the way we are writing, we are trying to give you certain understanding that error matrix or variance covariance matrix of X is nothing but the variance covariance matrix of the error source, which is E.
Sir.
Yes.
Sir, in left box, why this expectation of epsilon, that is epsilon is error, then why its expectation has become 0, sir?
अरे यार अभी तो बताया भाई, कौन बताएगा इसका आंसर? Who is asking?
Sir, me, Sumit Pandey.
हाँ भाई आलोक बताइए.
Sir, expectation of any error means to follow zero value. We want to achieve zero value in error.
Expectation अगर मैं आपसे कहूँ, you all have grown up now, but you must have listened to those old rhymes. Like, what is expected from a student? That it would become ideal student. It would, wake up at 4 a.m., do some study, go for jogging, do some fitness exercise, then come back, take the bath, do some puja, then take the breakfast. These kind of some ideal structure, isn't it? But now nowadays nobody follows it. Similarly, here the expectation operator is what is expected. Although we know that it is not true. In real scenario, error would always be there. It would not be 0. But what is expected from the errors? That it would be 0. The mean of the error would be 0. You get the point?
Yes, sir.
You try to look in the context of the terminology which we are at. The expectation is something which is beyond your control. You can expect anything. Okay, you can expect from Pakistan to behave properly as a democratic nation, but it's not true. They are real world. You have to bear the consequences, isn't it? Anyways, the error propagation in non-linear function. Okay, so obviously the non-linear function, we need to understand whether now this is the point where you need to understand that whether it is a linear function or non-linear function, your approach should be same. If your approach is same, you do not have to remember two things at a time. You just work with single function. That's why I started with non-linear function. The linearization using Taylor series expansion would become Z as function of x1, x2, x3. Again, same thing that we have written in the previous 2-3 slides. But I'm just zooming it a bit so that you would be stick to much more focused content. Now, the non-linear function from your BTech basics, you know that it is linearized by Taylor series expansion against some initial point. So those who have not comfortable with Taylor series expansion, they can go back after the class. They can read it from their books or online, wherever they're from. The Taylor series expansion is a way by which you can linearize a function in a certain up to certain order and with respect to some initial points. Please remember, two things are very important: linearization of a non-linear function, at the same time initial points, because linearization cannot be done independent. It has to be have some initial points. Then the Z1, then you write the so-called function value at initial point plus partial derivative with respect to first variable multiplied by the deviation, partial derivative with respect to second point multiplied by the deviation, so on goes up to n, partial derivative with respect to n, and the deviation. What is deviation? Deviation is the around the initial point, the x1 minus x naught, x2 minus x2 naught, x3 minus x3 naught, x4 minus x4 naught, like that. Okay. Similarly, for Z2, for Z3, for Zn, you are writing all set equation. Please remember, it's very simple. First, if you are given any function, let's say in this case it is very long, you just have two values x and y. Let's say, for example, instead of x1, x2, x3, xn, you simply have two values x and y. Z is a function of x and y. It is a non-linear function. How would you write it? You will start with f xy at the function value at x naught, y naught, that becomes z naught, plus del f xy by del x multiplied by x minus x naught, plus del f by del y multiplied by y minus y naught. The same way you are writing in an n dimensional. Okay, just take a look. For your information, I have just uploaded the lecture content of the previous classes, lecture 1 and lecture 2, part 1 and part 2. And there is also one supporting document to read about the one-dimensional, two-dimensional, three-dimensional error. So now you can follow the slides also. At the same time, it is quite advised that you should first read the book, because if you do not read the book, I mean, in two hours kind of session, I cannot speak everything. I have also a memory, I have also a content to cover. So it is advised that you should follow the books. Then at the same time, you can read the content from the slide. Okay, that would be much more good for you. Okay, I hope you are following it. So now you are representing Z1 again by writing Z1 naught plus J11. That becomes Jacobian. I don't know you are aware of this Jacobian term or not. Those are those who have little exposure towards partial derivatives. They must be knowing this term Jacobian. Jacobian is a term called for partial derivatives. So the Jacobian 1,1, Jacobian 1,2, function 1 and its derivative with respect to which variable? First variable. That becomes J11. Then again, function number is f1 Which one variable? Second variable, that becomes J12. Then similarly, J1n, that means which function? First function. Which variable? N variable. Partial derivative with respect to which variable? N variable. Or nth variable, I would say. J1n multiplied by delta. Z2 is equal to Z2 naught plus partial derivative of which function? Second function. With respect to which variable? First variable. Z21 multiplied by deviation plus Z22 multiplied by deviation. Similarly, all the content is written. Now, I will not change the slide to next. What I want from you, that now you have a function, isn't it? You have a function called Z1 is equal to Z1 naught plus J11 delta X1 plus J12 delta X2 plus J13 delta X3 or delta Xn. Similarly, Z2, Z3, Zn. What you can do now, you need to tell me what is the variance in Z1, what is the variance in Z2, what is the variance in Z3. Not consider the n variable for the time being, just take the three variables x1, x2 and x3. Now you need to tell me mu Z1 as well as sigma Z1 square or variance Z1. You need to tell me mu Z2 and sigma Z2 or variance of Z2. Then mu Z3 and variance of Z3 or sigma Z3 square. Take three variables x1, x2, x3. Take three functions z1, z2, z3. Do it. Now you have little background from your previous understanding. Let me see just if anyone can come up with the right answer or not. Just try to do it. Starting from, so hint number one, starting, take expectation on both sides. Start from there. Anyone with answer? अरे भाई बताइए, कोई आंसर तक पहुंच पाया? Okay, let us see how it is being done. So law of propagation says you have to make it function of y is equal to ax plus b kind of, isn't it? That's how you have started. So what we have done in the case of z1 up to zm, we have made it vector z is equal to z1 naught, z2 naught, they are all function values, they would be constant. Okay, so it becomes z naught plus all the Jacobians were taken out, and it is formed in terms of a vector. This is a wrong, it should be cross here, it should be cross here, it is not plus, it should be cross, strong. Just understand that it is a j vector, and then obviously the multiplied by delta x. Now the dimension m cross 1, it should be m cross n, and it is the delta x vector would become n cross 1. So the error delta z or dz would become z minus z naught, which is z delta x. Okay, so errors in z and x are relatively very small compared with absolute magnitude of z and x. We may approximate the infinitesimal differential dx and dz and dx by corresponding finite errors at ez and ex. So it's very simple that your way of represents. First, you learn how it is represented. See, the same equation is written here, but how you can convert from this kind of structure to this structure. It's very simple. How would you do it? You would do it by z1, z2 up to zm is equal to z1 naught plus z2 naught zm naught plus Jacobian set of matrix m cross n, and then multiplied by all delta x. Now, if one would want to go back to their previous set of structure, they can go ahead. They can multiply it. How would you multiply it? Z1, X1, Z12, X2, Z13, X3, Z1n, delta Xn. Then Z12, delta X1, Z22, delta X2, Z2n, delta Xn. That's how you do it. You can reach again to that same. But why it is important? Because since you have linearized it, you need to understand the moment you have linearized it, it is better you represent in a vector form like that. Z is equal to Z0 plus Z into delta X. Now it is a function of Y is equal to JX plus Z0, or Z is equal to JX plus Z0. That there's nothing but similarly similar fashion you can write it as Y is equal to AX plus B, isn't it?
Sir, is it like say equation of straight line y equals to mx plus c?
At this present, you can consider this as a equation of a straight lines or like that, but more or less, we are trying to linearize the non-linear system of equations. Okay. For our purpose of finding the error propagation kind of solution, because error propagation still we have not reached to that final answer. What would be the final output, or how would you write error propagation for any kind of function? We are still in the search of that. We are just moving ahead.
Sir, yesterday you have said that there are like sine wave is there a single line and error are by square of, you have shown a diagram.
No, that is different thing. That is among set of observation, you are best fitting it. Suppose you place a bunch of observation on Excel, okay, and then you best fit it. So how do you best fit it? Best fit by a line, best fit by a curve, isn't it? That's how you do it. If a set of observation is that we call it linear regression, isn't it? So what you can do, you can best fit those points by line or by a second degree polynomial, third degree polynomial, 5-degree polynomial. That's how you can do it. So if a polynomial is itself is given, what we can do, if we best fit a line, we can get the offset. This is what we have done in the yesterday, but here it is slightly different. Yesterday we have done to represent the geoidal undulation. How geoidal undulation would be computed? We have to take the normal from that geoidal surface onto the ellipsoidal surface. This was the way. But here it is slightly different. We are reaching towards error propagation concept final solution. This is just middle of it. Okay. Any question?